Okay, let's see if we can do the same kind of analysis that we did with selection sort in order to understand why it is that merge sort can work so much faster. This is a little bit more of a complicated analysis, but if you study it, it's kind of straight algebra. It's just you have to understand what's happening. So I'll try and walk us through the analysis of what's going on. So in order to do this analysis, what we need to do is, just like with selection sort, we need to consider how many times each element of our original array is visited. We assume that visiting the array is the chunk of work that needs to be done, and so we can analyze it based on visits that we make. All right, so we'll start with an array that has a length of size n, and we'll try and figure out how many times it's visited. In order to make this analysis easier, we're going to make an assumption about n, and we're going to assume that n is a clean power of 2. And so we can represent n, rather than using n, we'll say it's 2 to some power, 2 to the m. So it means that for this analysis, we're identifying that n is a number like 1024, which is 2 to the 10, or 2048, which is 2 to the 11. Now, once we've established that for our analysis, n is going to be a clean power of 2, we can look, based on the algorithm that we saw previously in that code snippet, exactly how many times are we going to visit our elements in our array. And we can work backwards on this because it kind of is a little bit easier to start with the merge part. So this first bullet here talks about the merging operation. And if we consider the merging operation, and we ask how many times does an array get visited in order to do the merge, there's 3 visits for every element in our array. We have to look at one element in first, one element in second. We need to choose the smallest and then put it into our final array. So those are the 3 looks that we have to do. We have to do those 3 looks for every element we end up putting in our final array A. And since there are n elements in our final array A, we need to have 3 visits for every element in A, or 3 to the n. So the process of merging incurs a cost of 3 times n visits. Now, now moving backwards to the beginning of the algorithm, we had to split our original incoming array A into 2 pieces. We had to split it into first and second. Well, that required 2 visits to every element in A. We had to look at an element of A and put it into first, and then the second element of A and put it into first. And then as we got to the second half of A, we had to put the second half of A into second half of A into second. So for every element that was in our original array A, we had to put it into first, and we had to put it into second. So that's an additional number of visits of our array of 2 times n. So far we have 3 times n visits in order to do the merge, and we have 2 times n visits in order to set up the 2 smaller arrays that we need to sort. So far it's a total of 5n visits. The thing that's not accounted for in this analysis is how much time does it take to sort those smaller 2 arrays that we created. And to do that analysis, we're actually going to do the analysis with a recursive formula. So let me set that up for us. Let's set up a variable tn, which is going to be a formula which captures the total running time of our algorithm. By using a recursive definition of 2 to the n, we can capture the total number of visits that we're going to incur by running the MergeSort algorithm. We know that t to the n is going to cost us t to the n over 2 plus t to the n over 2. That's the cost of sorting the 2 smaller arrays. Now we don't know what it is necessarily, but we know that we're going to have to sort the smaller array, and we're going to have to sort the second array. And that whatever cost is incurred by that is captured by t passing in n over 2. And then the work of splitting the array and the work of merging the array is 5n. So for any array of length n, we know that the cost is going to be 2 times t of n over 2 plus 5n. That's a pretty straightforward but recursive definition of our running time. And we can't solve it as is. And so what we need to do is we need to do a little bit more analysis. So let's say that we wanted to solve what t of n over 2 is. Well, what we're going to do is we're going to use the formula from the second bullet in the first paragraph here. And instead of plugging in n, we're just going to plug in n over 2. And we get a very straightforward textual replacement of the original n with now n over 2. And so we see from that that t of n over 2 is just t2 times t of n over 4 plus 5 times n over 2. All we've done is replace the n by n over 2. So it's just straight algebraic substitution. So if we look and then we want to, if we then take that analysis for what t of n over 2 costs, and we go back to the first bullet in the top section, we can plug in our result for t of n over 2 into that first equation. So we end up with t of n from our top bullet, but now we're looking at our third sub-bullet, is going to be 2 times what t of n over 2 is. Well, what's t of n over 2? Well, it's 2t of n over 4 plus 5n plus 5n plus 5n. Because we multiplied through that 2 from our top equation to the 5 over n over 2. So hopefully in the third sub-bullet there, you can see how we've taken t of n over 2 and plugged it into the equation from the second bullet. Well, now we need to solve for t of n over 4. Well, we can do the same thing. We can just textually put n over 4 into the second bullet from the top so that we get t of n over 4 is 2 times t of n over 8 plus 5 times n over 4. And if we then substitute that back into our third bullet, we see that t of n is now 2 times 2 times 2 times t of n over 8 plus 5n plus 5n plus 5n. As we recursively solve each of the smaller problems by dividing n by an additional power of 2, you can see that a certain pattern is emerging, where every time we split in half, we multiply by another 2 at the beginning, and we add another 5n to the end. Well, that gives us an ability, now we can bring our initial assumption about the size of n to solve this equation. If we repeat this process k times, then what we're going to end up with is 2 times 2 multiplied by itself by k times, so we can represent that as 2 to the k. The remaining piece that we need to recursively solve is now t of n over 2 to the k, and then the number of times that we've added 5n is k times. So the last piece is plus 5n k. That's just a way of representing splitting our array k times. Now we'll go back to our initial assumption. Our initial assumption was that n itself was a power of 2 to the m. So let's take that equation from our first bullet and just solve for when k equals m. Well, when k equals m, we just textually substitute through m for k. And we get t to the n equals 2 to the m times t n over 2 to the m plus 5nm. But we know something about m. We can relate m to n because we know that exponential power. So for starters, we know that t of n over 2 to the m is t of n over n, which is t of 1, which is a constant time. And so we know that the smallest level we get down to is t of n of 1 plus 5nm. Because, let me say that again. So t of m itself is n, so we get that at the beginning. T of n over 2 to the m is t of 1, that's that second component, and then 5nm remains as it stands. We can solve for m. We know m is equivalent to log base 2 of n. And so we get an overall evaluation for any size n, that's a power of 2, that t to the n equals n plus 5n log 2 base n. So now we want to know, what is the big O notation of this equation? Well, the way in which we do that is we look at all the components that are being added together, and we find the one that grows the fastest. The first component is growing linearly. It's n. Then we add a component that's growing superlinearly. It's growing n times log base 2 of n. That's better than n squared, but it's more than n. So to establish the growth order, we're going to drop the lower order n. We're going to drop the constant factor 5. We're going to drop the base of the logarithm because we know that all logarithms are related by a constant factor. And what we're left with is n log n. And so the big O notation, the growth order, the efficiency of MergeSort is order n log n. Now that has a big impact. The impact on that is the difference between an order n squared algorithm and an order n log n algorithm. So let's say that we have an array that is of length 1024. Well, our selection sort is going to take something like 1,000,000 time units, a little bit more than 1,000,000 time units. But our MergeSort algorithm is only going to take something like 10,000 time units. That's a huge difference. And the difference is just because of the way in which we wrote our algorithm. The way in which we manipulated our data through a pattern of writing code makes the difference between something that just can't feasibly be solved, a selection sort algorithm on a large data set, and brings it down into something that can be solved, as a sort algorithm on a large data set. N log n grows much more slowly than n squared. Here's a few data points to sort of describe that. If you look at the graph in red, those are data points for selection sort growing as n squared. And if on that same scale of axis you plot the time for MergeSort, it appears that MergeSort isn't growing at all. Now it is growing, but the rate at which it's growing is significantly smaller, as you can see by this graph. 60,000 elements, a typical application of selection sort will take 19,000 milliseconds, whereas MergeSort will only take 205 milliseconds. Now granted, it's not like 19,000 milliseconds is a super long time, it's just 19 seconds. But 60,000 isn't very large either. Imagine that you're trying to do this with, everyone's census record in the United States. That's going to not be sortable using selection sort in a reasonable amount of time. Okay, thank you for your attention. We'll continue thinking about sort in future videos.